Welcome to Part 5 of the Servo and Motion Onboarding series. Controlling a servo system isn't just about turning it on and off. It's about precision, flexibility, and choosing the right approach for the application. Different control methods allow for fine-tuned adjustments in movement, speed, and force, depending on system requirements. In this session, we'll take a closer look at how servo control works, the way signals are processed, and how advanced techniques enable complex motion tasks. Let's get started. Let's start with the most basic question. What are the different control modes in servo systems? Speed control mode allows the servo to maintain a constant velocity. The user defines the speed and sets acceleration and deceleration values to ensure smooth transitions. Once these parameters are configured, the servo automatically regulates its speed, keeping it steady regardless of external influences. Position control mode allows the servo to move to a precisely defined target position. This can be either a linear position, as seen in XYZ motion systems, or a rotary position, where the servo rotates to a specific angle. Using feedback from encoders, the system continuously monitors and adjusts the movement to ensure accuracy within the defined operating range. This makes position control ideal for applications that require high precision and repeatability. Torque control mode regulates the amount of force applied by the servo motor rather than focusing on speed or position. This is essential in applications where maintaining a precise level of torque is crucial, such as in tightening operations. For example, in this bottle capping process, position control is used for the initial fast tightening, while torque control ensures the correct amount of force is applied to prevent over-tightening or damaging the cap. Is it possible to use a gearbox in torque mode? When operating in torque control mode, using a gearbox may seem like a practical choice, but it comes with significant challenges. A gearbox introduces mechanical compliance and backlash, which can cause inconsistencies in torque transmission. Since torque control relies on direct feedback from the motor, any elasticity or play in the gearbox can result in delayed or inaccurate torque application. Additionally, gearboxes are designed to modify speed and torque ratios, which can interfere with the precise force regulation required in torque mode. This is why direct drive systems or solutions with minimal mechanical compliance are often preferred for torque control applications. In precise torque control, the ability to adjust torque in small increments is crucial. This depends on the resolution of the servo amplifier's current output, which in our amplifiers is 0.1% of the maximum current. Let's look at a practical example. Using a meshed RJ540 GRG amplifier with an HK Key 43 dub motor, the smallest torque increment we can generate is 0.45 M. However, when we introduce a 110 gearbox, this increment increases proportionally, reaching 0.045 M. This means that instead of fine torque adjustments, the system can only apply force in much larger steps, leading to reduced precision. This is one of the key reasons why using a gearbox in torque control is not recommended. The ability to precisely control torque depends on two key factors: the drive's capacity and the gearbox ratio. In general, increasing either of these factors reduces torque resolution. For example, if the smallest torque increment the drive can generate is 0.1% of its maximum torque, applying a gearbox with a higher ratio amplifies this increment proportionally. As a result, the system loses its ability to make fine torque adjustments, which is critical for precise control. This is why using a gearbox in torque control mode can lead to reduced accuracy and performance. When using torque control, it's important to consider how the combination of drive capacity and gearbox ratio affects resolution. A higher drive power and a larger gearbox ratio lead to a coarser torque resolution, making fine adjustments difficult. For example, a 5 kilowatts drive with a 130 gearbox results in a torque increment of approximately 2 M, a significant step size that limits precision. To avoid such issues, it's crucial to discuss torque resolution requirements with the customer and use proper calculations to verify whether the selected system meets their needs. The same concept that applies to gearboxes and torque control also applies to ball screws and other types of lead screws. However, instead of torque resolution, we need to consider force resolution, which depends on the screw's lead. The forced increment can be calculated using this equation, where ds represents the lead of the screw. A larger screw lead results in lower force resolution, reducing the system's ability to apply small, precise force adjustments. This is why careful calculation is essential when designing torque control applications with ball screws. Point table control allows a servo system to execute predefined motion sequences based on a structured set of positions or motion profiles. Each row in the table represents a specific motion command, such as moving to a defined position. To trigger execution, the corresponding input signal must be activated. For A-series amplifiers, the maximum number of rows is 255, which aligns with the amplifier's input capacity. Since there are 8 inputs, this results in 28 equals 256 possible states, with one reserved for the default 0 state. This method simplifies motion control, allowing quick execution of predefined moves with minimal programming. To summarize, achieving precise torque control requires careful attention to the servo amplifier's resolution and the gearbox ratio. Larger ratios or higher drive power result in coarser torque adjustments, reducing accuracy. This principle also applies to ball screws and other lead screws, where force resolution plays a key role. Proper calculations are essential to ensure the system meets the required precision. CLK/DIR control is a servo position control mode where the servo drive amplifier receives 2 signals from a controller, a pulse train and a direction command. This scheme is analogous to stepper motor step/direction control and is commonly used for simple yet precise servo motion control. It only requires 2 signals and avoids the need for more complex interfaces or continuous analog commands. Many PLCs and motion controllers provide pulse output channels, making it a cost-effective and straightforward way to control one or a few axes. Because of its simplicity and precision, this control mode is popular for systems that demand accurate motion execution without the overhead of networked or closed-loop analog control schemes. In analog control mode, A-version servo amplifiers allow both speed and torque to be controlled using an analog voltage signal. For speed control, the motor's velocity is adjusted based on an input voltage ranging from -10V to 10V, where negative values correspond to counterclockwise motion and positive values to clockwise motion. For torque control, the applied voltage determines the torque output with a typical range of -8V to 8V. Analog control provides a straightforward way to manage servo motion, making it useful for applications that do not require digital communication or advanced network integration. Servo control can be achieved using pulse or analog signals, where electrical signals are sent between the motion controller and the servo amplifier. Pulse signals are commonly used for position and speed control, while analog signals regulate speed and torque through a continuous voltage input. While this approach is a cost-effective solution, it requires more cabling between the controller and the amplifier. Additionally, only a limited set of motion parameters can be exchanged, making it a simpler but less flexible form of communication. Network-based control offers a more advanced communication method, where coded data is transmitted in structured communication frames using industry-standard protocols. Protocols such as CC-Link ETSN, CC-Link A-Field, SSCNATII/H, Profinet, and EtherCAT enable efficient and real-time motion control. Unlike pulse or analog signals, network communication requires only a single cable, typically optical or Ethernet, to transfer large amounts of data at extremely high speeds, often in the range of milliseconds or even microseconds. This makes network-based control ideal for complex, multi-axis motion systems where real-time coordination and flexibility are essential. This comparison highlights the key differences between fiber-based and Ethernet-based servo networks. SSCNATII/H uses optical fiber, offering low interference and high reliability, but with slower communication speeds and higher cable costs. It does not allow additional devices like I/O or HMIs to be connected within the same network. On the other hand, CC-Link ETSN utilizes Ethernet cables, supporting higher data speeds of up to 1,000 MAPS and faster cycle times. It also enables multiple devices to be connected within the same network. However, Ethernet networks require better shielding to minimize interference, especially when using longer cables. Choosing the right network depends on application requirements, balancing speed, expandability, and resistance to interference. Servo operation includes key functions such as homing and jog mode. Homing ensures the servo system aligns with its reference position. In an incremental system, this process must be repeated every time the machine is powered on. However, in an absolute system, homing is only performed once after assembly, unless power is lost without a backup. JOG mode provides manual operation, similar to the manual mode in CNC machines. It is used to test system movement, define the starting position, or make precise adjustments. This mode allows for continuous movement or inching, depending on the application's needs. There are many industrial field bus networks available on the market, including PRO5BUS, EtherCAT, and Ethernet IP. Mitsubishi Electric offers its own high-performance networks such as CC-Link IETSN, CC-Link IE Field, and SSC-NET-II/H, designed for fast and reliable communication in servo applications. How does PTP control work? In point-to-point, or PTP, control, the motion controller sends discrete position-based commands to the servo drive, which independently calculates and executes the movement. The controller transmits commands such as position, speed, torque, and acceleration, while the servo drive provides feedback, reporting actual position, speed, and torque. The refresh rate of these updates depends on the fieldbus communication speed, influencing the system's responsiveness and precision. How does motion control work? In motion control, fieldbus synchronization ensures precise coordination between multiple servo axes. The motion controller continuously transmits cyclic commands to each servo drive, defining their speed, position, and torque. At the same time, each servo provides cyclic feedback, allowing the controller to monitor and adjust movements in real time. This enables synchronized motion, making it essential for robotics, conveyors, and multi-axis automation. Servo systems can operate in point-to-point PTP control or interpolated control, depending on application needs. In PTP control, the motion controller sends position commands, but the servo drive calculates and executes the movement independently. This is ideal for simple, sequential motions. In interpolated control, the motion controller sends continuous trajectory data, enabling smooth multi-axis synchronization. This makes it ideal for robotics, CNC machining, and precision automation. A fieldbus network enables real-time motion control by continuously exchanging data between the motion controller and multiple servo drives. The controller sends cyclic commands, defining motion parameters like position, speed, and torque. The servo drives return cyclic feedback, ensuring accurate execution. This closed-loop communication allows for precise, coordinated motion, which is critical in high-performance automation systems. One of the key advantages of fieldbus-based motion control is its modularity and flexibility. In many systems, the number of motion modules can be adjusted dynamically, whether it's adding new axes, replacing existing ones, or even swapping modules as needed. This flexibility allows for scalable automation, where systems can be expanded or modified without requiring a complete reconfiguration. Such adaptability is especially useful in modern reconfigurable manufacturing and robotic applications. Cams. What are they, and why do they matter? Cams are used in motion control to convert rotary motion into linear or angular motion based on a predefined pattern known as a cam profile. This profile dictates how the system moves over time, ensuring precise positioning, smooth acceleration, and speed control. Cams are widely used in automation, packaging, printing, and robotics, where highly synchronized movements are required. By using electronic cams in servo systems, manufacturers can replace mechanical camshafts, achieving greater flexibility, accuracy, and efficiency in modern automation. Mechanical cams have long been used in traditional machines to generate precise motion patterns. A classic example is the crankshaft in an engine, which transforms rotational motion into linear piston movement, ensuring controlled timing and efficiency. However, mechanical cams have fixed motion profiles, making adjustments difficult. Modern automation systems now use electronic camming, allowing for flexible, programmable motion control, improving precision and efficiency in industrial applications. Cams and servo control are widely used in filling machines, where precise motion synchronization is essential. For example, In liquid filling systems, the outflow of water remains constant, while the filling head speed varies based on bottle shape and diameter. A servo-driven cam profile ensures smooth acceleration and deceleration, preventing spillage and optimizing efficiency. This method allows for high-speed, accurate filling, making it ideal for modern packaging and bottling industries. Servo control is all about selecting the right method for the job, whether adjusting motion dynamically or ensuring precise synchronization. Understanding how these systems operate is key to efficiency and performance. By using the right control strategies, servo-driven applications can achieve exceptional accuracy and responsiveness. Thanks for watching, and see you in the next session.